Well, thanks for hanging in there. My name is Bill Gervasi, and I'm a memory systems architect for monolithic power systems. In addition to that, I'm a chairman in the JEDEC standards organization. And among the tasks that I am involved with is the definition of the system management for memory subsystems. And so not coming from a storage world, you're going to see that there's a little different flavor here, but I believe it applies to what you're doing. Now, I'm going to be speaking on the easy topic, which is the data center where equipment gets obsoleted in a reasonable amount of time. My buddy here, however, is going to take on the hard question about automotive. So, quick overview here, and I have a funny feeling I'm preaching to the choir when we go through this material here, is that the explosion of the number of standardized interfaces, things like CXL and so forth, have just dramatically increased the number of attack points in the system. And the sophistication of the attackers are increasing. And so what we find is that the number of attacks keep increasing every year as well. That we have hardware level attacks like malware, man-in-the-middle, or even spy chips. On the software side, insecure agency, insecure plug-in design, insecure output handling, all of these mechanisms are being combined to come up with new ways to break into the system. I just read, I defined the SPD, serial presence detect, that's a configuration ROM that is on every memory module in the industry. And the paper that I read recently, I think it's called Bad RAM, says that they went in, found out that most people are not write protecting their SPD chips. And they're able to go in there and change the number of rows in the DRAM, which turns off half of the DRAM. It makes a 16 gigabyte module look like 8 gigabytes, and then they're able to put their spy code in that half of the memory module that is suddenly exposed. Simple little hacks like that are increasing in the industry, and we need to figure out how we're going to protect against those. So that's been my job recently. So a lot of this has to do with establishing a root of trust. And root of trust is going to become more important in this discussion because in the memory subsystems, we have a different set of rules. We don't have terabytes that we can live in. My serial presence detect chip is 1 kilobyte. And we have, memory module might have 50 intelligent devices on it. 40 of them are the DRAMs themselves, but we also have voltage regulators, we have thermal sensors, we have the SPD itself. All of these devices are attack points. And so we are facing a different class of problem because of this. And so the root of trust is going to be an essential part of how we're going to move forward with a secure system. So we're seeing a number of presentations back to back, and I think we're saying a real consistent message that security is a treadmill. That we keep chasing our tail on this, and we see that if you look at this timeline here, we kept increasing the sophistication of the algorithms. And these are based on the sophistication of the hardware that is available in the industry at large to attack our systems. However, this can come along and bite us. The fact that it is a treadmill caught me personally when I wrote the JEDEC Automotive SSD specification. And literally 3 months before I was going before final approval of the specification, NIST generated a memo saying that especially for automotive applications where the vehicle is going to be in the market for a very long time, that 256-bit algorithms were going to be deprecated and that it was time to move to 384-bit. And so at that time, we went into the task group, had that discussion. realized, and brought the car manufacturers into this as well to discuss this, came to the conclusion that, yeah, this was the right time to change it before it got into the marketplace. So we literally rewrote the specification and delayed introduction into the industry by some 3 or 6 months in order to make that change in the security. But that's an important lesson about where we are in terms of trying to keep up with an ever-changing standard. So the realization that we have, and especially now that we're working on the DDR6 generation of products in the industry, is what are we going to do about the fact that security requirements are going to change? Nothing that we pick today will be valid in 2040 when DDR6 is still shipping. So we need to be flexible. We recognize that there's going to be combinations of hardware, firmware, interactions between the devices, the BMCs, the hosts, and so forth. So we wanted to tackle all of that. So with the entering of quantum computers, and here's the timeline that Paul was referring to, is that by 2030, NIST is deprecating the use of the legacy algorithms, and by 2035, the disallowing of the legacy algorithms. So Paul is exactly right. You start counting back from there that if you have a 5-year depreciation cycle on something, in 2030, you better have already made that transition. If it's a 2-year qualification cycle prior to that, again, it's 7 years.
And for what it's worth, I checked my presentation. I simply skipped over that slide that has all the details. So you can find it there too.
Yeah, but we have a consistent message, which is good. So you look at this algorithm here. And I think 2 presentations ago, we saw a simplified version of this. I included the full handshake there. And this is just opening the door. This is not even the exchange of the real data. Just opening the door is this massive exchange of information over a 6 megahertz system management bus. And it's a very complex handshake. So what does this mean for a memory assembly that has 50 devices on it that are all attack points? Are we going to replicate this, which comfortably and conservatively is estimated at, say, 4,500 gates plus 16 kilobytes for the certificate? Are you going to replicate that in all 50 devices on a memory module? And price of a DRAM is basically a $5 or $10 chip. What are you going to do to the price of every DRAM in the system? What are you going to do to the price of a thermal sensor, which basically sells for somewhere around 7 cents? Are you going to put this on that thermal sensor? And so the conclusion that we came to is this is just not practicable. We cannot add this to the bill of materials for all 50 components on an assembly. So we had to do something. We looked at proxying, and the feedback that we got from customers was that proxy was not going to work. And by proxy, I mean, what if we put the security algorithms on one chip, like the SPD, in that module and had it proxy the rest of the module? And the feedback was, all it takes is for somebody to copy the serial number out of any one of those other 49 chips, and you've lost the game. So where are we going to go? What are we going to do if that's not going to work for us? And the answer that we came up with is bill of materials. That we are hooking ourselves onto a different treadmill, which is how do we validate and establish a reasonable root of trust that can be revalidated over time. So you take this information about how an assembly is put together, and you have the module manufacturer code and part number and so forth for every one of those 50 intelligent components on the module. And now what can we do with that? Well, this is where we've engaged with a number of standards bodies, CISA, NIST, and DMTF on establishing a framework for establishing root of trust. And I have some links at the bottom here in the presentation so you can follow up on these things. But essentially what it says is that we need to figure out the source of every memory module in the system. And what do you do with that information? What you're going to do is do a discovery phase to figure out what it is that's plugged into your system. You establish a connection to the supplier and ask the supplier what is on that. So you establish the trust between the end user and the supplier using something like blockchain. So blockchain implements the security mechanisms by which you get to the supplier of the assembly. And as blockchain evolves and adopts the PQC algorithms, that's how you stay on the treadmill of becoming safe, where you have the room to put your PQC authentication in one place. It makes the whole subsystem more affordable. Now, this requires those of us that are supplying parts to the industry that we now have support for these mechanisms, that we have a hardware bill of materials that's in a standardized database schema that can be processed by the end user. Once you get that blockchain link to the supplier, you download the entire bill of materials. So now this says that if I buy a memory module from Micron and it contains a voltage regulator from MPS and it contains a DRAM from Micron, and it contains a register from Montage, whatever that combination of components on that assembly are, that all of that is detailed, and you're going to replicate this entire chain for everything on the module. And so these nested links are going to get you down to these other components. Put a quick snapshot of what the database schema looks like. And this is just a subset of that, but you can kind of get a sense for what the categories are. They're capturing the finished goods assembly information, the information about component parts, and even things about what process node was used to build the silicon devices. So I have a personal criticism about this. Yeah, John.
I understand what I heard in Vancouver a bit more now. So in the system, is every component going to be at least validating its serial number and its information, where the blockchain information itself is stored in what I would call the FRU, or in whoever is actually the root of trust?
Yeah, I'll go through that in the next slide. One of the criticisms I do have about this, though, is that as we did the analysis in JEDEC about what data we wanted collected, one of the key things that was brought up was that end users wanted to see all the way down to the individual part serial number, and to require that each part have a unique serial number. And why is that a significant variation from what NIST and CISA have come up with? Is that they only narrow it down to a specific manufacturer in a specific factory in a specific week. That could be 1 million parts. What you want to be able to build are exclusion lists. And you can't build an exclusion list for 1 million parts. You want an exclusion list to be that a specific part has been spoofed, so that now you can sniff through your data center and find out if that part was duplicated in other places.
What protections exist against tampered devices? A legitimate part that was created, sold, maybe even deployed, and then later was removed and then modified with something that may not identify itself. So in the case of DDR memory, there are exposed buses that are not cryptographically protected at the DIMM level. Maybe at the system level they are, but not at the DIMM level. Right. What is being done to identify and say, this device has been tampered with? I think the answer is nothing.
That is a correct reading of that.
Okay.
And so And that's, again, gets to the importance of an exclusion list, that if you do get spoofed, that it becomes a one-time event as opposed to something that's replicated throughout your data center. So that, in particular, you might get that Micron module, your Micron identifier tells you which blockchain to establish, so you make your blockchain connection to micron.com. Micron responds with, oh, we happen to know that those modules have been hacked in the industry. So Micron can give that alert. Or if it's a Google that's using that Micron module, Google would own the responsibility for adding into their databases that such a device has been spoofed. But it is not, it was determined to be unfeasible that you could protect all 50 devices on the module, which was the only absolute point. And even then, man in the middle is still possible. Well, if you don't have a mic, let's keep the mic here, or, yeah.
The concern is if the part was tampered with en route, it left the manufacturer fine, it got intercepted, something happened to it, then got deployed without anybody being aware. So although this is an improvement, and this is a it's an improvement, so I don't, it's a good thing, but it is not an end-to-end solution. And there are some notable gaps, especially when it comes to tampering. If you're looking at protecting profits and avoiding counterfeits, this is good. If you're trying to avoid state actors, this is insufficient.
And I'll point out the same thing applies to beyond DRAM module. It also applies to an SSD, that all it takes is to replace one of the flash chips on an SSD. You have exactly the same exposure. That's right.
I had another question.
Yes.
First, well played on the barcode. Yeah. Secondly, is this intended to be limited to security items, or if there's, say, a factory excursion and this is a walking wounded unit or something, could that also be this exact same method for excluding certain serial numbers or notifying a customer?
Yeah, absolutely. That this can be a two-way street, where if this can be a mechanism by which Micron broadcasts ECNs. And then going the other direction, it's not just limited to smart components. It could be all the way down to which capacitors were used in that assembly. And one of the things that I'll get into in a minute here is that an increasing number of sophisticated systems are deploying AI-based telemetry engines that can detect that they had a capacitor short or a capacitor catch fire from X manufacturer, and then again build not an exclusion list so much as maybe a telemetry entry into the AI engine that can then go out there and say, what other modules and in my system use that particular component that is having to trend towards failure. So it also involves telemetry processing. So here's an example of how this process works. For example, with the memory module, the first thing you do is you suck down out of the memory module in its configuration ROM the module supplier and that link. You establish the link out to the module manufacturer, who responds with the bill of materials, and then individual devices, as much as detail as you want to dig into, you can collect information about this. Now, the good news is, while this is time consuming and it does replicate that exchange chain that I showed, this is something you probably only have to do the first time you boot the system, and maybe you have a rolling reanalysis every once in a while where you go out there and revalidate the hardware in your system. So it's not the kind of thing that has to happen every single time you boot a system. But spoofing is still possible. And so we are still going to need to be able to do predictive elements in this. The other thing I'll point out is that software has the same issue, and it's even bigger, because if you're updating firmware out there, you have, again, the NIST guidelines on how to do firmware updates, but you also want to validate the same thing. Are you getting the replacement firmware from the right source, and so forth? So the SBOM requirements are very, very similar to the HBOM requirements, and they are a superset of the HBOM. So, yeah, the basic message is that establishing the root of trust is not a foolproof system, but it's something that gives us a grip on controlling our inventories. And none of this is free. I think, in fact, I know I'm preaching to the choir here, is that we're all paying for the cost of implementing these systems, but it's cheaper than fixing the problems after they happen. So with that, let me head it over to my buddy.
Thank you, Bill. So Bill just talked about the application in the data centers. And nowadays, actually, I'm going to talk about a new trend in the automotive, which is now the vehicle is basically the data center on wheel, right? So you're going to see a lot of new features, which is cool, but is actually giving you additional problem for the security. Let's see. So what's the difference when the storage components, goes into the cars? In the very beginning, is about the lifetime. The lifetime, different from the consumer devices or data centers, is going to be super long. So basically, the lifetime is going to be over 10 years, 10 to 15 years. You'll still see many old cars on the road, manufacturing really good, right? And you're going to see the harsh thermal electrical environment. Basically, you're going to see a huge variation of the temperature from minus 40 degrees C to 125 degrees C. You're going to see a lot of transient surge, EMC issues. Another is the safety. We call it the ASIL requirement, automotive safety reliability. This is the real-time response that a car has to be safe. Otherwise, nobody's going to drive it. And another challenge is the supply chain, as well as the update cycle, is super slow compared to other applications. So the security must be resilient from day one. And now, the HPC is actually putting the memory and storage device as the heart of the car. You see, we saw some super chips are driving up the memory demands in the vehicle, starting from maybe at the entry-level ADAS application, which require SoC needs 20 TOPS. Now, so if you would like to achieve the real level 4 or level 5 autonomous driving, you need a much powerful superchips that is actually over 100 watts and need to meet the safety level of the ASIL-D, which is the highest level of the safety. And this is actually bring a lot of information, a lot of opportunities for the hackers. Because now, with all those high-power computing chips in the vehicle, the modern-day vehicle is transforming to software-defined vehicles. We call it SDV. You're going to enjoy a lot of flexibilities. You're going to see many over-the-air OTA updates, and you're going to see fancy features. You're going to see a hardware and software ecosystem, and you try those fancy EVs, especially in Asia. You're going to see huge numbers of features and apps that help you to make sure you enjoy the vehicle as your living room. And this is big data and their fast software development as well. Those car makers is actually hiring a lot of software guys to developing all those features. But all this opened the gate for the security problems. That's why I put a hacker image on the backside of those benefits that the EV car makers are advertising, right? And here, the storage and the memory is everywhere inside the SDVs. And if we look at the architecture for modern-day EVs, it's no longer a domain control base as GM or Ford or even Mercedes usually do. It's called a zonal architecture. Basically, there is a huge central compute processing all those information from the sensors like radar and cameras. And you have different zones. For example, the right zone, left zone, front zone, and rear zone basically control and do local processing for those informations. For example, the radar and the cameras first pass the information into the zonal architecture. The zone ZCU, the zone control unit, processing the information and feeds the central compute, whatever the result is. And you really want to have this zonal architecture because if you feeding everything into the central compute, basically you really need a huge computing power, which is for now not affordable for a vehicle. But this is actually, making more memory usage, not only in the center of the car, but also in those zonal controllers. More memory usage, more potential tasks can be happen. And SDVs means a lot of software updates. If you guys own a Tesla, you're going to see they push the updates again, maybe every quarter. They do software and firmware updates. And in that case, they still use the same hardware. Basically, you cannot change the hardware immediately. So the DDR must maintain the security for a long time. And there is a gap for the memory security, as Bill mentioned. Same challenges in the data center, but it's even worse in automotive. You're going to see that spoofing, roll hammer, man in the middle, you name it. Yeah, it's all valid in automotive. But one thing that makes automotive special is the user, the owner of the car, can also be the hacker. So basically, you're going to have the vehicles in your garage. You can do whatever you want, and no one can stop you. And if all the vehicles, even from the same manufacturer, share the same algorithm, and for the security, the hackers can detect them and understand all the algorithm behind it, which make the security gap even bigger. And we talk about the SPDM. This is a great start, but it's not sufficient. It works well in the data centers for the servers, but it's still spoofable in some cases, like cloned serials. That's why the BOM is very important to verify the components, as Bill mentioned. And it also requires a frequency updates. We talk about a lot of algorithms. Maybe in 5 years, some algorithm can no longer be used. In 10 years, some of the algorithm cannot be used as well. So requalification for those devices in automotive is a big headache. You see in automotive, you need to run really long qualification cycles, sometimes over a year to qualify one IC, one semiconductor devices to use in the automotive. And we also talk about the quantum threats. And it's possible that the automotive might be the first application under attack because the car shipping today in 2025 may still be on the road in 2040. So the PQC-ready hardware for memories and other storage devices, security boot likely appear. Yeah, in robotaxi first. We see the announce of the robotaxi last year from Tesla. Those cars may still on the road in 10 years. And the storage vendors need to consider the future-proofing hardware level trade-offs basically now. And we identify there is a missing link between those huge computing powers like GPUs and the storage devices. Basically, the memory today has no strong identity verification at boot. If they're compromised, SoC cannot distinguish the genuine memory and the spoofed memory. So basically, there needs to have a new trust anchor. So ideally, close to the physical connections of the SoC and the memory. Again, it's not only for the central compute of the vehicles, even the zonal architecture, which have the zonal processing power facing this missing link as well. And PMICs, once afterthought, can actually make data security better. So basically, the PMICs is already sequenced the memory power through the I3C. So the PMICs providing the power for the SoCs, for the GPUs, for all those storage devices is actually a great natural location to enforce the security policy before the memory or the storage data become accessible. And you know, PMIC is really have a low-level access, which means this is a strong control point, not easy to be hacked. And we got the idea about a PMIC with embedded SPDM plus the PQC. So basically, the PMIC going to perform the SPDM handshakes with the host and the memory. And it can also store the certificate hash keys, implemented the PQC algorithms we talk about. And this is allow memory access only after this authentication passes. That's why you can see here, this is actually control in the middle before those GPU SoC memories even become powered. And we see a lot of benefits, especially for the storage vendors. In the first place, we can offload the SPDM PQC complexities from the memory module because qualify a memory module for automotive taking super long time. And there is no need to requalify the DIMM or SSD every security cycles. Yeah. Basically, the security can be upgraded via the PMIC firmware, not hardware redesign. And it also enables the modular design for automotive and the end zones. And where this technology can be applied first, we see maybe the SSD could be the first use because the requalification cost for a SSD unit for automotive is super high. And the DDR, LPDDRs for the SDV, software-defined vehicle SoCs, may be one of the key targets for this idea because they need the high speed and security is especially important in those applications. However, the security landscape is not yet developed. So we talk about a lot of algorithms. We talk about so many software engineers is developing new features for the new EVs. But now it's still like this barren land on the left side of the screen. So basically, there is no unified approach that guides us to make sure the security gap is closed. This can only be done if the memory vendor, SoC vendor, PMIC vendor, developers, the OEM car makers are working together. So basically, standardize is very important in automotive, and it's always important to make sure we have a security vehicle. So just a quick recap on this. So basically, now the vehicle is changing. It used to be a world ruled by mechanical engineer. Now all the new features is driven by those super chips. It's turned the vehicle into a data center on wheel. And there's a lot of more memory usage in the software-defined vehicles lead to more potential attack for the vehicles in the future. And the automotive requalification is a huge headache for the automotive industry, and in the future, maybe a huge headache for the memory vendors and for the developers as well. And post-quantum threat, automotive application could be the first. And the PMIC with embedded SPDM plus the PQC could be a good solution to meet this challenge. But again, in order to make sure we are future ready, collaboration is important. So that's why we call action to collaborating with memory vendors, with developers, and all the standard institutions work on this together. And thank you for your listening. Any questions?
Yeah, first about, and you may have mentioned this, security for over-the-air updates. I find that terrifying. It's a huge attack surface. What is done to secure that? Is it simply ensuring that the private key used to sign the firmware update remains secret?
Yeah, actually now the way that the OEM doing the over-the-air updates is really simple, just a secure keys. And even for some, I won't name the car maker's name, some of the OTA for the Asia OEM, they actually don't have much security, much algorithms during they release that. So this is a big problem, and actually the government is also discuss some of the standard to make sure the OTA has been done in a correct way.
Okay. Let's see. A question about the right to repair. I certainly, as somebody who is enraged by the price of repairs at Toyota, I certainly understand why people would want to be able to repair their own cars. On the other hand, I see the point of view of the manufacturers. What is the legal liability if your customer does a repair and that either gets in compromised software, or they do it themselves and they screw it up and the change causes them to be killed? Is there any protection for the manufacturer if the customer chooses to repair and screws up the repair on the car? Does anyone know what the legal environment is?
That's a very good question, but to be honest, I don't know the answer for this. Yeah, I believe the legal department for those car makers, is putting a lot of terms to make sure you fully understand, even though we never read it.
Yeah,
we
that's right. You click through
right?
it. Yes.
Yeah. But for
Okay.
sure, they protect themselves in a really, really, sure.
Yeah, to respond to that from the data center side, we kind of have that same problem, right? People can unplug a CXL module, plug a replacement module in, and the centers are going to want to validate it, and so that the lockout of replacement is going to be a prolific issue for cars, for data centers, and it's a very common problem that if it has to balance across this, exactly as you say, the right to repair. That if somebody puts in their own repair unit, it needs to pass this qualification in order to be accepted into the network. Otherwise, it will be seen as a foreign attack.
Right.
And so I'm not a lawyer, fortunately, so I'm not sure how that's going to play out.
Okay. Just one final comment. You referred to a data center on wheels, or with the entertainment, a living room on wheels. Reminded me of in high school a driver's education instructor referring to a car as a bedroom on wheels.
I was actually going to reply to your earlier comment. If you follow the DEF CON crowd much, there has actually been a lot of effort there, and legally what most of the car manufacturers are doing is you are leasing the computer system from them. So by, well, at least the software side of it. So by doing anything not in the normal operation of the car, you're hacking back, essentially.
You're voiding your warranty?
Yes. Not just voiding your warranty, you're voiding all of the security and reliability statements for the car.
In other words, you're assuming liability yourself.
Yes. Well, even more than that, the comment was that you're assuming liability yourself. Even more than that, you are then not just voiding the warranty, but it is considered hacking of a system that you do not have access to.
Now, to put that in context, though, I do want to be able to hack into my wife's car to change the GPS so it says, "Girl, I told you to turn right."
Yeah. Or if you're not going to take the directions I'm giving you, I'm going to shut up. Okay, so now hacking, that sounds like it's a violation of the law. You're, you're committing a felony by changing it, which seems to fly in the face of the intent of the right to repair. So it sounds like it's unresolved at this point.
There's active legal cases going on right now. The big popular one is John Deere. Right. Yes. Also, some car manufacturers have, crap, I'm blanking on the word now, but like a HackerOne program.
Well, even the modification of e-bikes.
Yeah.
The modification of an e-bike to have it go beyond the legal definition of, what is it, level 1, 2, and 3 operation.
Yeah.
What law are you breaking? And
Yeah.
is that going to change in the lifetime of that vehicle?
Bug bounty programs, that's what I was thinking of. Yeah, I know, was it Jeep famously did one after they had a bunch of stunt hacking? Yeah, but we can talk after.
Are there any other questions? Then thank you for your attendance, and let's call it a week.
Thank you.